Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 4, Integrals. Section 4.9 and 5.4, Antiderivatives and the Indefinite Integral.
Lesson 2, the power rule for integrals.
And now we're going to go on and try to figure out some rules to help us find integrals. It's hard sometimes to just think backwards each time and think, well, what do I have to start with so that when I differentiate it, I end up with what they are asking me to integrate. So what we're going to do is try to develop some rules of integration that help us to do that thinking backwards process a little bit more easily. And the first rule we're going to try to discover is the power rule for integrals. Well, you may have already noticed that the integrals that I gave you were rather convenient. For example, we integrated 5x to the 4th dx, and that was nice because we got an x to the 5th plus c as an answer, and that was a nice, neat answer. And yeah, when I differentiate x to the 5th, I do get 5x to the 4th. But you may have noticed that this is kind of a contrived problem. It had this 5 very conveniently in the problem that I gave you, and that was important because when you differentiated, the 5 got pulled down in front. Well, what if I had just asked you to integrate x to the 4th rather than 5x to the 4th? Okay, well, I know because of the way that we differentiate powers of x, I know this has to be an x to the 5th power, because I'm going to be reducing this exponent by 1 when I take the derivative using the power rule for derivatives. But we know that even if I add an integration constant on here, it's not going to be the right answer. So this is sort of a guess, but I'm pretty sure that that's wrong. And I could check that it's wrong by differentiating it and saying, oh, okay, well, if that's correct, then I'm going to go ahead and differentiate this. But because we've done this same differentiation before, we end up with 5x to the 4th plus 0, so we get 5x to the 4th. So I have this really annoying, I'm going to put annoying factor of 5 in here. And this just isn't the right answer, because when I differentiate it, I get this extra 5. I just want x to the 4th. I don't want 5x to the 4th. So somehow we're going to have to come up with a function here that undoes this extra factor of 5 that's in here. And I'm going to put a little box in front, and what we're going to do essentially is fill in that box with what you could call a fix-it factor. And I want you to think for a moment, what constant multiple could I put in the box so that when I do differentiate my full answer here, it gets rid of this annoying factor of 5. And if you guess what that is, it would have to be a 1/5. Because 1/5 times 5, those are going to cancel out and give me just a 1 in front of my x to the 5th. So we need a fix-it factor in there. Now let's check. We said that our original guess didn't work. Now we have a new guess. So let me try my new guess. So I am guessing, I'm going to check it in green. I claim this is the right fix-it factor to have used, and let's check, and I think you'll see pretty quickly that that should fix up our answer. I am now differentiating 1/5 x to the 5th plus c, and when I differentiate the first term, I have a constant multiple of 1/5. So differentiating, we get to carry that constant multiple along, and now I take the derivative of x to the 5th, this part of it, and I get the 5x to the 4th. There's that annoying factor of 5 that I didn't like, and of course the derivative of the constant will just be 0. And does that work? That looks great, because you notice that the 1/5 times the 5, those undo each other or cancel each other out or give you a factor of 1. And so I end up with x to the 4th plus 0, or x to the fourth. And notice this is great because it matches what I was originally asked to integrate. So this matches. And that means I've found the correct answer. And my correct answer is not x to the fifth plus c, but rather 1/5 x to the fifth plus c. So we had to have that fix-it factor in there to get rid of the annoying factor of 5 that we were getting. Well, I'd like you to pause the video and see if you can figure out the integral of x to the 9th dx in a similar way. Okay, well, let's try this one together. When I look at x to the 9th, it's still a power of x. So because of the power rule for differentiation, I know that my answer has got to have an x to the 10th in it. That's the only way when I use the power rule, I will end up with one lower exponent here. I'll end up with an x to the 9th, which I can see is what I want. But if I try this as a guess, x to the 10th plus c, and check it, very quickly I will figure out that that guess does not quite work. And why doesn't it work? Well, if I do it over here on the side, the derivative of x to the 10th plus c would unfortunately be 10x to the 9th plus 0. So I have, again, this annoying factor of 10 that's coming into my answer. I'm supposed to get x to the 9th, and I'm getting 10x to the 9th when I go back and check my answer. So this guess is not quite right. So what did you do to try to fix that up? What fix-it factor could go right in front of the x to the 10th so that it would work out correctly? Well, hopefully you saw that because you want to get rid of a 10, you need a 1/10 out in front. And you can check that. Let's check it in green. I'm saying this is now my correct answer, so I'm hoping that's no longer a guess. But let's check it. And if I take the derivative of 1/10 x to the 10th plus c, the 1/10 gets carried along. It's a constant multiple. I use the power rule for derivatives on this part. Pull down the 10, x to one lower power, so x to the 9th plus 0, and yay, these factors cancel out. The 1/10 times the 10 becomes a 1, and I end up with x to the 9th. And that does match the thing I was originally asked to integrate. And so since it matches, it means that my guess is no longer a guess, it's the right answer. Okay. So let's try to come up with a rule in general so that we don't have to think quite so hard each time we want to find the set of antiderivatives of a power of x. And what we're going to write down now is the power rule for integrals. Remember, we already had a power rule for derivatives that said if you have x to the n, you pull the n down, and you have x to the n minus 1, x to 1, an exponent that's 1 lower. So we're going to do the same sort of thing for integrals. In other words, we're going to find a power rule for the set of all antiderivatives of a function that is a power of x. So here I have the integral of x to the n, where n can be any real number. There's one real number actually that we'll have to exclude, and I'll talk about that over here in a moment. But we have the integral of x to the n dx. And let's go ahead and start to think backwards, but once we've done it once, we won't have to do it over and over again. So think of n as being any constant power on our x. Well, just like we said here, if we started with x to the 4th and we were asked to integrate that, we needed a power that was 1 higher. We needed an x to the 5th. When we had x to the 9th, we needed an x to the 10th. So if I have an x to the n, what power will I need on my x? I'll need it to 1 higher power so that when I differentiate, I'll get back to x to the n. So I would need it to n plus 1 in general. So if this is a 4, x to the 4th, I'm going to need an x to the 5th here. Now, what am I going to need in the way of I'm going to put my integration constant on there, plus c. What am I going to need in the way of a fix-it factor in front? Because if I were to just differentiate at this point, let me just kind of do that over here on the side. if I were just to differentiate x to the n plus 1, and I'm going to put parentheses around that n plus 1, plus c, that would not quite work, right? Because when I differentiate, I pull the n plus 1 down, and then I would have x to the n plus 1 minus 1, and then the derivative of the constant would be 0. This exponent will be good because I'll have n plus 1 minus 1. Those 1's drop out, and I'd get an x to the n, but then I have the annoying n plus 1 that's out in front. So what fix-it factor do I need out in front here so that I will end up canceling this annoying factor of n plus 1? Well, just like we did in these specific examples here, I need a 1 over whatever my new power is. I need a 1 over n plus 1. Because after all, when I differentiate it, I'm going to be pulling this factor of n plus 1 down to the front. Okay, so let's go ahead and see if that works out, and then I'll talk a little bit about the exclusion on what n I cannot use. I'm claiming that this is right, and if you want to put parentheses around this n plus 1, it might help a little bit in terms of checking it. So let me check and see if this actually works, and I think as we check it, if you weren't convinced before, you'll be convinced that this is correct. So if I claim these are the set of all antiderivatives, it's easy to check by just taking the derivative. So let's do that. So remember that n is a constant. So this is a constant. If we're talking about a power function, it's x to some constant power. So n plus 1 is a constant. And that means 1 over n plus 1 is a constant multiple of x to the n plus 1. So when I take the derivative, the constant multiple of 1 over n plus 1 gets carried along. It'll be that constant times the derivative of x to the n plus 1. We actually did that over here. You pull down the power, so I have an n plus 1 in the front, and you have x to the n plus 1, and then to 1 lower power, so I'm going to subtract 1 from that, and then the derivative of our integration constant is just 0. Well, did our fix-it factor work? That looks pretty good because I have an n plus 1 times a 1 over n plus 1. Those multiply out to be just a factor of 1. And so I would end up with x to the n plus 1 minus 1. And notice that 1 minus 1, those drop out or add up to 0. And so I get x to the n. And that looks good because that matches the thing I was originally asked to find the integral of. So these two things match. I should underline this whole thing. I get x to the n, the very thing I was asked to integrate. So this looks like the right power rule. Okay, so these two match and we're all set. However, remember I mentioned that this general power rule works for any real number n except there's one value that we have to exclude. And maybe by looking at the rule that we've developed here, you can even tell what the value of n would give us a problem. If you look at the answer over here, there's one value of n that would give us trouble, and that has to do with this fix-it factor that we had out in front, 1 over n plus 1. This fix-it factor has a problem when n is equal to -1, because you notice that if n happened to be -1, I get 1 over -1 plus 1. And what's the problem with that? I get -1 plus 1 would be 0 in the denominator. So if I were to try to use the power rule on that particular value of n, I would run into trouble. I would end up with a fraction out in front that looks like 1 over 0. So we'll go ahead and look at this in more detail on the next page, but the power rule works great on every constant power of x except the power x to the -1. So that's the one value we can't use the general power rule on. And you might wonder, well, how do I figure out what the integral of x to the -1 is? And let's go ahead and see if we can check that out. So, remark, I said n can't be equal to -1, and why not? And if you were to just to go ahead and try this, you might just blindly go ahead and try to use the power rule. That would be fine. And you say, oh, okay, well, my n is equal to -1, so I'm going to do x to 1 higher power, so I'm going to do -1 plus 1, and so I would need a 1 over -1 plus 1 down in the denominator, and then I'll put my plus c. If you just blindly try to apply the power rule, I think you'll see very quickly that you get 1 over 0. That's what we were talking about on the last page. X to the 0 is fine. That would just be equal to 1. But 1 over 0 is unfortunately undefined. So 1 over 0 is undefined. And so, problem. This is not giving us an answer, it's just giving us a set of functions that are all undefined. So how do I find the integral of x to the -1? Well, let's write it in a way that probably is more familiar to you. Instead of x to the -1, the integral of that, I'm going to write it as 1 over x dx. Just rewriting this with a positive exponent would be 1 over x to the +1, which is 1 over x. And do we know how to integrate 1 over x dx? Yeah, you actually did that a couple of pages back. The integral of that is simply the natural log of absolute value of x plus c. So you get a really totally different kind of answer. Here we get for the power rule, we get a power function as an answer. So if I go back to the last page, when I integrate a power function, I get another power function or a set of power functions as an answer, but not when x equals -1. The power rule doesn't work if you blindly apply it. I think you'll hopefully notice, wait, I'm getting 1 over 0, something's wrong. So then just rewrite x to the -1 as 1 over x, and I think you'll recognize that as the derivative of ln of absolute value of x plus c. So that's the one value of n that we can't use the power rule for. However, we already happen to know the antiderivative of x to the -1. It was just not a power function as an answer. It's ln of absolute value of x. Okay, well now what I'd like us to do is just a bunch of examples where we get used to using the power rule. And we'll see that in certain cases we have to actually rewrite the function first before we find the integral of the function or the set of antiderivatives of the function. So let's start with this one, x to the 15. So I'm asked to integrate x to the 15 dx. I want to find the set of all antiderivatives, and I'm just going to put the power rule, I'm going to place it right on top of here from the last page so that we have that to refer to. So in this case, notice that the n in the power rule is 15. So when I use the power rule for this, I will write down my x, and I want x to 1 higher power. So I'm doing 15 plus 1. My n is equal to 15. And so I will get x to the 16th power. So that is my new power on x. And then notice that I need a fix-it factor that is 1 over n plus 1. So this 1 over 15 plus 1, it's going to be 1 over 16. The way that I do it is I figure out what the new power is by adding 1 to the old power, and then I do 1 over that new power out in front. So I do 1 over, my new power is 16, so 1 over 16 out in front. And then don't forget to add your plus c, because you're going from one answer to an infinite set of answers when you add that plus c. So that's usually the way that I do it, or you can just think, my n is 15, I want 1 over 15 plus 1, that'll be 1 over 16, and then x to the n plus 1, that would be 15 plus 1, or 16. But for me, it's easier to figure out the power on the x first, and then do 1 over that new power out in front. If I want to check that, how do I check? Same way we always check, and that is by differentiating, and you can either do it in your head, if it's fairly simple, or you can write it out. And we'll do the check on this one, but I think I'll leave the other checks for you. Remember, when we differentiate, this 1 over 16 is a constant multiple, so that gets carried along. And then you're just finding the derivative of x to the 16. That's 16x to 1 lower power, 15, and the derivative of this constant is just 0. The 1 over 16 and the 16 multiply to give me a 1, so those cancel out, and I do get x to the 15, which was the thing I was originally asked to integrate. So why don't you stop the video and try the next two, and then maybe we'll do the third one together. So do the next two, and then if you get stuck, we'll go through it together. Okay, so let's go ahead and look at this next one. I'm asked to integrate t to the 30th dt. Don't get thrown off by the fact that we're using a different variable. It doesn't matter whether you use an x or a t. Integration works exactly the same way. Just like when you differentiate, you can differentiate a function of x with respect to x, or you can differentiate a function of t with respect to t. Exactly the same principle holds when you're finding antiderivatives. So I just go ahead and say, okay, the only thing I want to be careful about is that my base is going to be t, and I want t to 1 higher power. My n is 30. I need an n plus 1 here, so that would be 30 plus 1 would be 31. And then I need a 1 over the new power out in front, so a 1 over 31 out in front, and then put a plus c on the end. So 1/31 times t to the 31 plus c, and that would be my answer. Again, I could check it. I'll leave you to do the check there. Did you try this one? It's the integral of just x dx. Of course, you could just think backwards on this, but let's try to use the power rule and see if we can figure it out that way. This doesn't exactly look like a power of x because there's no n here, but what would the power on the x be? X is the same thing as x to what exponent? X is the same as x to the first. So there really is an n there, we just don't write it. So my n in this case is equal to 1. So my n is equal to 1 in this case. And that means that when I go over here, I'm going to have x to 1 higher power. So I have to add 1 to 1. That would be 1 plus 1 would be 2. So I need an x squared over here. Then my fix-it factor of 1 over that new power goes in front. So I would have a 1 over 2 in front, and then I add a plus c. And you can check if you want to, either mentally or write it out. I have 1/2, and if I were to differentiate, that 1/2 would get carried along. I differentiate x squared and get 2x, and the derivative of c is just 0, and 1/2 times the 2, those cancel out, and I do end up just getting x as an answer. So I'll let you do that check. Let's look at the last one. Now this one I wanted us to do together because I want to warn you that this power rule works when you have x raised to some number. It says nothing at all about what happens if you have 1 over x raised to some number. So this is really a quotient of two functions here. And in fact, there is no quotient rule for integrals, the way there is a quotient rule for derivatives. But it is possible to rewrite this. Can you think of how to rewrite this so that it is x to a power? 1 over x cubed would be, here's my sponge, the same thing as x to the -3rd power. So it's possible to take the function they're asking me to integrate and to rewrite it as a power of x. As soon as I rewrite it as a power of x, x raised to a number rather than 1 over x raised to a number, I get to use this power rule. So now I get to go ahead and use the power rule. Be a little bit careful because you're working with a negative number in the exponent here. So we're going to have x to 1 higher power. And remember, that means we're taking -3 and we're adding 1 onto that. So I'm actually ultimately going to get x to the -2 here. And then I'll have to add my plus c onto the front. And then I need the fix-it factor out in front. So my new power is -2. I need 1 over that new power out in front. So I had x to the negative 3, I add 1 to negative 3, I get negative 2, and I need 1 over that new exponent out in front. So I had a 1 over negative 3 plus 1 out in front, which is 1 over negative 2. Okay, the only thing that I don't like about this particular answer is that I have a negative exponent, and we usually like to rewrite our final answer with only positive exponents. So I want to rewrite this in equivalent form, but one that doesn't contain a negative exponent. So just keep in mind that this would be the same as, I'm going to put the negative in front of the fraction, negative 1/2 times x to the negative 2 is 1 over x squared plus c. And usually we would write that as minus 1, just multiplying these fractions together, minus 1 over 2x squared plus c. And that would be a nicer way to write the final answer because it would not contain a negative exponent. Okay, let's go ahead and have you try another one. Actually, let's do the one that's at the top together, and then I'm going to give you a couple to try. So suppose I'm asked to integrate square root of x dx. Is that a power of x? It doesn't look like it initially, but remember that you could again rewrite it before you take the derivative. And how could I rewrite root x so that it's x to a number, so that it's a power of x? Well, remember the square root of x is the same thing as x raised to the 1/2 power. So it is possible to write roots of x as power functions. So this is x raised to a real number, so that's x to the 1/2, so I can use the power rule. And let me go ahead and just remind you again of what the power rule is. I'll write it down here. We said it's integral of x to the n dx. I just want it to have on hand to refer to as we go through these. It'll be x to the n plus 1 with a 1 over n plus 1 in front plus c. So just keep in mind that there's our power rule to refer to again. So let's go ahead then and think about what our n is in this case. In this case, our n is 1/2. So that's our n. And when I figure out what my new power is, I have to do 1/2 plus 1. So unfortunately, I have to do some fractional arithmetic. And then I'll have a plus c out in front, and I'll have 1 over whatever my new exponent is out in front. Okay, well, let's figure out what all of this stuff is. X to the 1/2 plus 1, 1/2 plus 1 is the same as 1/2 plus 2/2. That would be x to the 3/2. So my new power is 1 higher than 1/2, which would be the number 3/2, or the fraction 3/2. Out in front, I need 1 over my new power. So it's going to be 1 over a fraction. It's going to be 1 over the fraction 3/2. And then I add on my plus c. Well, 1 divided by 3/2, if we invert and multiply, is the same thing as the reciprocal of 3/2. So it's the same thing as 2/3 x to the 3/2 plus c. So one way that some people like to think about it is that whatever your new power is here, whatever your new exponent is, this thing that's in front, the factor that's in front, is the reciprocal. It's 1 over, so it's the reciprocal of the new power, or the new exponent. So you notice that's what happened here. We add 1 to our exponent, we get our new power, and the number that ends up in front is the reciprocal of that new power. The reciprocal of 3/2 is 2/3. Now, one other thing I'm going to mention before we leave this particular example, and it's just a convention. we were given the problem with the root notation rather than the fractional exponent notation. And just like with derivatives, if the original problem was written with a root, we usually like to write our final answer with a root rather than a fractional exponent. I would probably accept this as a final answer, but we could also write it in root form. So let me just mention that a slightly nicer answer would be to write this as the square root of x raised to the third power plus c, or if you wanted to, you could write square root of x cubed and put the cubing inside the square root. Either way is okay. And in fact, if you think about it, square root of x cubed, I'll just do this on the side, would be the same thing as square root of x times square root of x times square root of x. And when we combine two of these together, if x is a positive or a non-negative value, I should say, which it has to be for our original function to be defined, we can't take the square root of a negative, these two things actually combine to give me an x. So you could even write this in an even more simplified form by saying, well, square root of x cubed, two of the square roots of factors of square root of x combine to give me an x, and then I have one factor of square root of x left over that I can't do anything with. And this would actually be the very nicest form for the answer to that problem. I'll put a little smiley face there. That would probably be the nicest form for your final answer. But I would probably accept an answer with a fractional exponent, or even with a root that isn't completely simplified. I would accept all three of these as final answers. It just depends on how picky your particular instructor is. Okay, I want you to think about this one, integral of the fourth root of w dw, and then if you can do that one, try integral of the fifth root of t squared dt, and if you get stuck, just restart the video and we'll go through it together. Okay, well, let's try those, and I'm going to just draw a line here because this is really all part of the previous problem so that we can kind of follow this. So again, this doesn't look like a power of w as it stands, but we could certainly write it as a power of w. The fourth root becomes which fractional exponent on w? It's the 1/4 power of w. So the fourth root of w can just be rewritten as w to the 1/4. And as soon as I do that, I can go ahead and apply my power rule because I've written this problem as a power of w. So now my n is 1/4. So keep in mind that my n is the number 1/4. So I always like to figure out the power on w first by doing 1/4 plus 1. And then I fill in everything else. Well, I'm just going to put some boxes here and a plus c. So let's see, if I do 1/4 plus 1, that's 1/4 plus 4/4, that's 5/4. So I get w to the 5/4. And I'm supposed to have 1/5/4 out in front, or another way of saying the same thing is I'm supposed to have the reciprocal of 5/4 out in front. 1 divided by 5/4 is the same as 1 times the reciprocal 4/5. So the factor that goes in front is always the reciprocal of whatever your new exponent is, and that would be 4/5. And then just don't forget your plus c. And again, if you want to, you can rewrite this in root form because our original problem was given to us as a root form, the fourth root of w. So it would be slightly nicer to rewrite this as 4/5, and I'm taking the fourth root. Remember, the denominator of our fractional exponent tells us what root to take, so it's the fourth root of w raised to the fifth power. You can either put the 5 in here, or you can take this whole thing and raise it to the fifth, and then plus c. And again, if you want to, remember this is really the fourth root of w multiplied by itself 5 times. When you group 4 of those together, the fourth root of w times the fourth root of w times the fourth root of w times the fourth root of w, you will actually get a w that comes outside of the root. and you would have 1/4 root of w left over plus c. This would be considered really the very nicest form to have your final answer in. So I'll put a little smiley face there, but I would probably accept this answer or this answer or this last answer. Any of those are okay. Well, hopefully you had a chance to think about this one too. It's the integral of the 5th root of t squared dt. So you just have to remember how to translate a root of this type, a root of a power, into something that's a pure power. So let's go ahead and try to write this as a power of t. Remember that whatever power I'm raising t to becomes the numerator of our fractional exponent, and whatever root I'm taking becomes the denominator. So it would be t to the 2/5. And now we just go ahead and apply our power rule. So I need t to 1 higher power. I'm thinking in my head 2/5 plus 1, that's 2/5 plus 5/5, so that's going to be t to the 7/5. And I need 1 over that new power out in front. In other words, the reciprocal of that power out in front, so that would be 5/7, and then just remember to add on your integration constant. This problem again was written originally with a root rather than a fractional exponent, so for that reason I would rewrite it with a root. And let's see, this I could write as the 5th root of t raised to the 7th power, or the very nicest way to write it would be to simplify that. When I put 5 factors of the 5th root of t together, I get a t, and I would actually have the 5th root of t squared left over, and we usually put it under the root. So that would be actually the very nicest form to have your final answer. But any of these 3 would be acceptable. Okay, let's look at the last example on this page. It looks a little weird because all I have is an integral sign and the dx, which is part of the operator that says find the set of all antiderivatives of whatever function is inside. And there's really no function inside. But you have to kind of know what the convention is, what we would mean if we just write the integral of dx. And what we mean by that is really the integral of 1 dx. Think of it as 1 times dx, which would be the same thing as dx. But that's something that you actually just have to be told, I guess the first time, that what you really mean by that is that you're integrating the function 1 dx, and you can think of that as sort of a multiplication. 1 times dx, it's the same thing as dx. But because we don't yet know where this symbol comes from, and it is just a symbol to us right at this moment, it's hard to see why we would interpret it necessarily that way. So when you see integral of dx, we will really mean the integral of the function 1 with respect to x. So the function I am trying to integrate is just the function 1, and I want you to think about doing this in 2 different ways. One way is simply to think backwards and think, what do I have to start with so that when I differentiate it, I end up with 1. And yeah, what do I have to start with? I have to start with x. And when I take the derivative of x, I get the function 1, the constant 1. And of course I have to add my plus c on. So one way to do this is just to think backwards, the way that we did our earlier problems. Think backwards. But the other way to do it would be to actually apply the power rule. So let's do it applying the power rule. So I'll say, or we could do it this way. If I want to find the, I'll just say or here, if I want to find the integral of 1 dx, I could write the number 1, that function, as a power of x. Well, what power, what exponent do I need on the x in order to make it equal to 1? Well, x to the 0 is the same thing as 1. So you could actually rewrite this constant 1 as a power of x. So that would be actually another way to do it, and that's why I included it in this set of exercises. And just to show you that it works, we know this is right. If I take the derivative of x plus c, I will get 1, and the derivative of c drops out. But let's just prove that it really works. What I'm doing is applying this power rule up here where my n is equal to the number 0. Well, the power rule says I take whatever my exponent is, 0 in this case, and I add 1 to it. 0 plus 1 would be 1. And then I want to do my fix-it factor, 1 over my new exponent out in front. So 1 over 1 is what would go out in front. And then I just add any c onto that. And you notice I get exactly the same answer that I got thinking backwards. So the power rule does work even on the exponent of 0. The only exponent it doesn't work for is the exponent -1, as we discussed earlier. Okay, so the next thing that we're going to talk about is